Next set of reactions involves adding carbocations, and in two forms, as alkyl groups and as acyl groups. So let's start with the first type, which is the Freidel-Crafts alkylation. So the Freidel-Crafts alkylation involves benzene, adding benzene and a an alkyl chloride, RCl, in the presence of aluminum chloride, which is a Lewis acid catalyst, just like you've seen with the previous reactions where we used Lewis acid catalyst. And the product would be, let's redraw that, an alkyl benzene. So you added an R group. The R group here can be a primary, a secondary, or tertiary alkyl group. So let's begin with the first step. The first step is making the electrophile, as always. So what if we have secondary or tertiary electrophiles? So you would form a carbocation. So let's look at it. So suppose we have C attached to 3 methyl groups. That's a tertiary carbon. It's C-butyl chloride. So in the presence of aluminum chloride, the chlorine will attack the aluminum. It's a Lewis acid, so it has an empty shell. And then the following product would result. Let me just make this a little bigger here. So once again, you see similarity here. Where again, there's a negative on the aluminum and a positive on the halide. And in this case, it's the chlorine. So what would happen here is that this would dissociate. So just like that. And then you would form, and we're going to need a little bit more space. So when I say I need more space, it's kind of like a chef who needs more salt. So that's the idea here. And we have a positive charge. Plus, of course, the AlCl4 minus. So this is your carbocation if it's a tertiary in this case. Same thing with a secondary. However, if you have a primary, you do not form a primary carbocation. So you would actually keep it, and we're going to show you in the next step, attached. So if I have something like this, an ethyl bromide. So this right here is a primary. And of course, the attack would take place in the same fashion. The only difference here is that instead of dissociating the group, the chloride and the aluminum chloride group, you keep them attached. You keep them this way because that's what's going to take place in the reaction, is that it's in this form. So do not dissociate. You keep it that way because that's your electrophile. Very well. So then in the next step, is nothing that we haven't covered already. You probably know what's, if I stack these right there, you probably know what to do next, and you should. All right, let me clean up a little bit here. So what do you think happens at this step? So there's a pattern, right? So the benzene is going to attack the carbocation. We use the tertiary here. So it's going to be big drawing it here. So we're actually going to just shorten it with CH3. You're already familiar with the condensed formula. And then there's a positive right there. Of course, you're aware that there are +2 resonance structures. Very well. So in the, if you have the, so this is for the secondary or tertiary. If you have a primary, then the reaction is going to be slightly different in terms of the benzene attack. And that is simply because primary is not as stable as a tertiary carbocation. So that's why it rather has the octet, even though in this weakened form, than actually without an octet. So the attack is going to take place here, and that would be your leaving group. So very well. Okay, notice how I attached this. I understand that sometimes even at this level, these mistakes can be made, but you should not. I attach it from the CH2, not from the CH3, simply because that violates the octet. If you have a CH3 here, it means it has 5 bonds. So in both steps, again, remember this one has also 2 resonance structures. I'm just going to write this. The last step is for both would be the same. So you'd have the Cl, AlCl3 minus Cl, AlCl3 minus, and it would take place this way. You have to move it from the bond, not from the lone pairs. It would be wrong from the lone pairs, because what do you think is going to happen? Now the Cl is going to have another H attached to it, and then it's going to form another complex. So that's not what happens. What happens is that the chlorine chooses to form a bond with hydrogen. And of course, for this, you would have the CH2, CH3 as your product, plus HCl, AlCl3 is back. And then for the top one, I'm going to erase the two resonance structures. If you wrote that, and just show you the product, which is simply CH3, 2, 3. This one is 3 actually. Let's go back and fix this. This one is 3 actually. Very well. So I will just circle your products so you can see them. You added the tertiary alkyl group here, T tert butyl, and then you added the ethyl in this case. Now, we may run into a problem here. In fact, could be a big problem, is that carbocations like to rearrange. If you recall that from organic 1, is that there was a methyl shift or a hydride shift, specifically hydride shift. So Freidel craft is susceptible to this carbocation rearrangement. And let's look at an example right here. So if we take propyl chloride and react it with benzene, and if you're aiming to make propyl bromide or chloride react with benzene and make propyl benzene, you would probably be disappointed, because this would yield only 35% yield. It's very depressed, it's very low, versus you would form this product at a 65% yield. Basically, for the 65% product, the reaction took place at the middle carbon. So that indicates that there is a shift. So this was a primary, and it became a secondary. And this was a secondary, it became a tertiary. What I mean by this is that at this point, it was a primary carbocation, but it shifted, became a secondary carbocation, and then, or it actually made a secondary alkyl product, versus this was a secondary, and after the reaction took place, it became a tertiary alkyl group, an alkyl compound with a benzene, because there's a carbon right here. So the question is, how does that take place? So there is a mechanism for rearrangement. For secondary and tertiary, and we're going to draw an example of a secondary and a tertiary. So what we have here is we have a secondary alkyl chloride. When the reaction takes place with the electrophile, to make an electrophile with the Lewis acid, notice what happens. And I'm showing this H for a reason. Once again, we know that this is positively charged, this is negative, so the bond is going to break, and then you would form the following. Okay, so if we look at this right here, I'm going to use red here. This is a secondary carbocation. You have a carbon here with two other carbons attached to it. That's what secondary means, and that's where your positive charge is at. Well, your molecule is not going to accept this result if there is a chance uh, of making this carbocation a tertiary. And it's right there in the vicinity. If you look at this H, this hydrogen, if we shift it along with its electrons, that's called a hydride shift. Just take this bond, remove it, and place it between now that carbon, where the carbocation was, and this hydrogen. Notice what happens. And I'll show the H just so you can see where it is. So notice now what you have. What you have now is a tertiary carbocation, which is more stable. So that's what happens with rearrangement, is if there is a chance that you can make the carbocation more stable by increasing the carbons around where that positive charge is, then you should take that opportunity. So very well. And for primary, also that happens. So if we have CH3, CH2, CH2, Cl, we're just going to draw the the step that led to this. So once again, what's going to happen is that if this breaks as an intermediate, I know I said it shouldn't, but the molecule is going to be wise enough to know that, in a sense, that it has a chance of making and I'm going to draw one of the H's on the second carbon. positive right there. So you shift because you would go from a primary to a secondary carbocation, which is following. And that explains why it's 65%, because look at where the attack would take place. Let me clean this up a little bit. Let's put it nicely. It's not as easy drawing with this, but you see exactly what I'm talking about, is that, again, the attack would take place at the secondary carbocation because, again, it's more stable, explaining why you would have a 65% yield versus a 35% yield. So again, we want to say is that this is a secondary carbocation. This is a primary. So it's more stable. So you have to be aware of this. You have to make sure that you do this rearrangement if the reaction is going to take place. So you go with a major product, unless when we get to synthesis where we will only work toward forming only a primary alkyl group attached, of course, to the benzene. But if you try primary, it will make your secondary alkyl attached instead of the primary attached. So keep that in mind, and we will explore this more in class.